In this episode, we're going to make gradients and derivatives feel like the practical steering mechanism behind model training rather than a purely mathematical topic that lives in a calculus classroom. When people hear derivative, they often picture complicated symbols and fear that they will have to do long calculations. But the key idea you need for the CompTIA Data AI exam is much simpler. A derivative tells you how a quantity changes when you change an input, and a gradient is the multivariable version of that idea, telling you how a result changes when you nudge many inputs at once. In model training, those nudges are the adjustments you make to a model's parameters, and the result you care about is the model's loss, meaning how wrong the model is according to a chosen measure. Training is the process of reducing loss, and gradients are the information that tells you which direction reduces it. By the end, you should be able to explain why gradients are the engine of learning, what it means to follow a gradient in a controlled way, and what can go wrong when gradients are noisy, unstable, or misused. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful way to ground this is to treat model training as a search problem where you are looking for parameter values that make predictions align with reality. Every model has parameters, which are internal settings that control its behavior, like weights that determine how strongly a feature influences a prediction. When you choose parameters, you can evaluate how good that choice is by computing a loss value, which increases when predictions are wrong and decreases when predictions are right. If you could test every possible parameter combination, training would be trivial, but the parameter space is usually enormous, so you need a guided way to move toward better settings. This is where derivatives matter, because they describe local change. Instead of guessing a new parameter set blindly, you can ask, if I change this parameter slightly, does the loss go up or down, and by how much? That local sensitivity information lets you adjust parameters in a direction that reduces loss. Beginners sometimes imagine training as a mysterious ritual of tuning, but it is fundamentally a controlled process of using change information to make step-by-step improvements. Gradients turn training into an informed walk downhill rather than a random wander. To understand derivatives without heavy math, it helps to picture a simple curve where the horizontal axis is a parameter value and the vertical axis is the loss. The derivative at a point is the slope of that curve at that point, meaning how steeply the loss rises or falls if you move a little. If the slope is positive, moving to the right increases loss, so moving to the left would decrease loss. If the slope is negative, moving to the right decreases loss, so moving to the right is good. If the slope is near zero, you are on a flat region or near a minimum where small moves do not change loss much. This slope idea is the essence of derivatives in training. They tell you which way is downhill locally. When you have many parameters, you cannot draw the full landscape, but the gradient gives you the slope information in every parameter direction at once. Beginners often think gradients are complicated objects, but conceptually they are just a list of slopes, one per parameter. The gradient is your map of which small changes will reduce loss most efficiently. Now let's connect that to gradient descent, which is the basic training strategy that uses gradients to improve a model. The idea is straightforward. Compute the gradient of the loss with respect to the parameters, then update the parameters in the opposite direction of the gradient. The opposite direction is used because the gradient points toward increasing loss, like the uphill direction, so moving against it moves you downhill. The size of the update is controlled by a learning rate, which is a step-size choice that determines how far you move in response to the gradient. Beginners sometimes hear learning rate and think it is a measure of intelligence, but it is simply a control knob for stability and speed. If the learning rate is too large, you can overshoot the minimum and bounce around, or even diverge, meaning loss gets worse. If it is too small, you can make progress painfully slowly, especially in flat regions. The exam often tests this qualitative understanding because it is one of the most important practical ideas in training. You do not need to compute updates numerically to explain why the learning rate matters. You just need the downhill walking picture. Loss functions deserve attention because gradients only make sense in relation to the loss you chose, and that choice defines what learning means. A loss function encodes what you consider wrong and how you punish wrongness, and different tasks use different losses for good reasons. In regression, losses often penalize the size of prediction errors, while in classification, losses often penalize confident wrong predictions heavily to encourage correct separation. The gradient is the derivative of the loss. So if you change the loss, you change the gradient landscape and therefore change the training dynamics. Beginners sometimes treat the loss as a technical detail, but it is the rulebook that defines success. If the loss is poorly aligned with the goal, the model can train very effectively toward the wrong objective. Exam questions may describe a mismatch between training objective and desired outcome and ask what the consequence is. The correct reasoning is that training will optimize what it is told to optimize, and gradients will faithfully drive the model toward lower loss even if that does not match the real-world metric you care about. Understanding this prevents you from assuming training always produces the behavior you intended. Another key idea is that gradients are local, which means they tell you what happens for small changes near your current position, not what the best global move is. This matters because loss landscapes can have complex shapes, including flat plateaus, steep cliffs, narrow valleys, and multiple local minima. A local minimum is a place where the slope is zero in all directions nearby, but it might not be the best possible minimum overall. In many practical machine learning problems, finding a perfect global minimum is less important than finding a good solution that generalizes, but the local nature of gradients still shapes how training behaves. Beginners sometimes think gradient descent is guaranteed to find the best possible solution, but it is better to think of it as a method that follows local slope information to find a low-loss region. The path it takes depends on where it starts, how the landscape is shaped, and how the learning rate is set. Exam questions might probe this by asking why different initializations can lead to different outcomes or why training can get stuck. The correct answer often involves local structure and the limitations of local information. In real training workflows, you rarely compute gradients using the entire dataset at once, because that can be expensive and because it can produce updates that are too smooth to escape certain traps. Instead, gradients are often estimated using subsets of the data, which introduces noise into the gradient. That noise can sound bad, but it can actually be helpful because noisy gradients can shake you out of shallow local minima and allow exploration of the landscape. At the same time, too much noise can make training unstable, causing the loss to bounce around and making it hard to converge. Beginners sometimes think noisy training means something is broken, but some fluctuation is normal when using partial data for updates. The important concept is that gradient estimates can be imperfect, and training methods balance efficiency with stability by choosing how much data to use per update. Even if you never name a specific algorithm, you can explain the trade-off. More data per update gives a more accurate gradient but costs more computation, while less data gives faster updates with more randomness. Exam questions may describe loss values that fluctuate during training and ask whether that is necessarily a failure. A mature answer recognizes that some noise is expected and that trends matter more than single-step changes. Because gradients are derivatives, they depend on the model's ability to produce a smooth enough relationship between parameters and loss, and that is why differentiability matters. A function is differentiable where small changes in input produce predictable changes in output, which makes slope meaningful. If your model or loss includes hard, abrupt decisions, the derivative can be undefined or unhelpful, which complicates gradient-based learning. Many models are designed so that their training time computations are differentiable even if their final predictions involve thresholds or discrete decisions, because training needs smooth signals. Beginners sometimes wonder how models can be trained with gradients if classification outcomes are discrete, and the answer is that training uses smooth surrogate losses that provide continuous feedback. The model learns from probabilities or scores during training. Then those scores can be converted into discrete labels for evaluation or deployment. On an exam, if you see language about using a differentiable loss, it is pointing at this idea. Gradients require smooth feedback. Without smooth feedback, you cannot reliably follow the slope downhill. Understanding this explains why gradient-based training is so widely used and why certain design choices in models exist. Now let's talk about what can go wrong, because the exam often tests failure modes and not just ideal behavior. One failure mode is vanishing gradients. where gradients become extremely small, making updates tiny and learning slow or stalled. Another failure mode is exploding gradients, where gradients become extremely large, making updates huge and unstable. Even without naming these terms explicitly, you should understand the concept that if slopes are too flat, you cannot find the direction to move effectively, and if slopes are too steep, you can overshoot and lose control. These problems can happen due to model structure, scaling of inputs, or the way errors propagate through layers in more complex models. The learning rate also interacts with these issues, because a large learning rate amplifies the effect of large gradients and can worsen instability, while a small learning rate can make small gradients even less effective. Exam scenarios might describe training that makes no progress or training that becomes unstable and ask for a likely explanation. A correct answer often involves gradient magnitude issues and step size control rather than vague claims that the model is just bad. Another important failure mode is getting a model that fits the training data well but performs poorly on new data, which is overfitting, and gradients can contribute to this by making the model extremely good at minimizing loss on the training set. The gradient descent process does not know about generalization by itself. It only knows about reducing the loss you computed on the data you fed it. If the model is flexible and training is allowed to continue without constraints, it can learn patterns that are specific to the training set, including noise. Beginners sometimes think training longer is always better because loss keeps going down, but that can be misleading if the loss is only measured on training data. A model can become more and more specialized to the training set while becoming less useful for new cases. This is why evaluation on separate data matters and why regularization-like ideas exist, even if you are not implementing them here. The exam may ask why training loss decreasing does not guarantee improvement, and the correct reasoning involves the difference between fitting seen data and generalizing to unseen data. Gradients are powerful at fitting. Your job is to make sure fitting aligns with generalization goals. Gradients also connect to the idea of feature scaling and representation, because the geometry of the loss landscape depends on how parameters interact with input features. If one feature has a much larger scale than others, gradients related to that feature can dominate updates, causing training to focus on that feature disproportionately. This can slow convergence or produce suboptimal solutions because the model takes steps that are too large in some directions and too small in others. Even in simple cases, poor scaling can create a loss landscape that is long and narrow, like a ravine where the downhill direction is hard to follow without bouncing side to side. Beginners often interpret slow training as a sign that the model is weak, but it can be a sign that the parameter space geometry is poorly conditioned. Scaling inputs and using appropriate learning rate strategies can make gradients more balanced, which leads to faster and more stable progress. On the exam, if a question hints at features with dramatically different ranges causing training issues, the hidden story is often that gradients are being distorted by scale. This ties back to vectors and norms, because training is happening in a multidimensional parameter space where step size and direction matter. It is also useful to understand gradients as signals of sensitivity, because that helps you interpret why some parameters change more than others during learning. If the gradient for a parameter is large, it means the loss is sensitive to that parameter at the current state, so changing it can produce a big effect. If the gradient is small, it means changes to that parameter produce little effect, at least locally. This can be because the parameter is already near a good value, because the parameter is irrelevant given the current representation, or because the model is stuck in a flat region. Beginners sometimes assume every parameter should update equally, but that is not how learning works. Learning focuses effort where it produces the most immediate improvement. This can produce interesting behavior, like early training focusing on course patterns and later training fine-tuning smaller adjustments. Exam questions may describe training where some weights change rapidly and others barely move and ask whether that is necessarily a problem. A mature answer recognizes that parameter updates reflect gradient information and that uneven updating can be normal. The key is whether the overall loss trend and generalization behavior are improving, not whether every parameter behaves identically. Finally, connect gradients back to the broader theme of model training as iterative improvement under uncertainty. Training data is imperfect, labels can be noisy, and the model's capacity can be too high or too low for the task, but gradients provide a systematic way to improve within those constraints. They tell you, given the current model and current data, which direction reduces loss, and repeated updates gradually shape the model into something that captures patterns. The process is not magical, and it is not guaranteed to find a perfect truth, but it is a powerful method for fitting a model to evidence. This perspective is important for the exam because it helps you interpret training outputs and troubleshooting scenarios in a grounded way. If the loss stops improving, you ask whether gradients are too small, whether the learning rate is too small, or whether the model cannot represent the pattern. If the loss becomes unstable, you ask whether gradients are too large, whether the learning rate is too large, or whether data issues are producing chaotic updates. If training performance improves, but real performance does not, you ask whether overfitting is occurring and whether the evaluation setup reflects reality. In every case, gradients and derivatives provide the underlying language of change that explains what you are seeing. When you can reason with that language, you are no longer guessing about training. You are interpreting it. To close, applying gradients and derivatives where they matter in model training means you understand that learning is driven by sensitivity information, not by mystery. You learn that derivatives describe how loss changes with small parameter changes, and gradients collect those slopes across all parameters to guide learning in a multidimensional space. You learn that gradient descent uses this information to step downhill, and that the learning rate controls the size of those steps, creating a trade-off between speed and stability. You learn that loss functions define what training optimizes, so choosing the wrong loss can produce a model that is optimized for the wrong objective even if training looks successful. You learn that gradients are local and can be noisy when estimated from subsets of data, which explains why training can fluctuate and why initialization and landscape shape matter. You also learned common failure modes, including stalled learning from tiny gradients, instability from huge gradients, and overfitting where training loss improves while generalization worsens. Most importantly, you built a practical mental model that gradients are the steering wheel of learning, telling you which direction reduces error and how sensitive the model is to different parameters. With that model, you can interpret training behavior, choose reasonable explanations for what goes wrong, and answer exam questions with steady, mature reasoning rather than fragile memorization.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.